Hi there, my name is Kevin Stamp from PS Motion. I would like to tell you a little bit about MechDesigner and how we can use it to design a cycloidal gear reducer. Now, MechDesigner is normally used for modeling complete machines with all the mechanisms interacting, with all the motion design and cams, etc. But here found and thought about a little application where we could use the power of MechDesigner to model the cycloidal gear reducer and especially the uh, lobed rotor that is the important part of the cycloidal gear reducer design. So, listen in, hope you enjoy it. For those that don't know what a cycloidal gear reducer is, from the front view you might imagine a shaft at the center rotating with an eccentric disc, and we'll just describe the motion of the front lobed cam, and that is orbiting around the center of the shaft by virtue of the eccentric, and it's rolling around the inside of some stationary pins in the what would be the machine frame or the stator of the gearbox. And so that disc is slowly rotating, but it's also wobbling. So one of the tasks is to get out the rotating motion and eliminate the wobbling part of the motion. And we do that by cutting holes through the discs and engaging it with a set of pins that are on the output rotor. And the output pins rotate at constant speed without the wobble action. Now if you introduce two eccentric wobbling cams, if you like, or cycloidal cams, then you can have two sets of holes in the middle of them, and that will, one, balance the mechanism or the gearbox a lot better, so you don't have one disc moving eccentrically. You can have one equal and opposite, but also you can provide more output capacity to drive the output pins on the output shaft. So if I just spin the model here, you can see this shaft rotating fairly quickly and the output shaft rotating quite slowly. So this tutorial is intended to describe to you how to model this fairly easily in MechDesigner. If I zoom in, you can zoom in and see the individual lobes, and how if I just increment the model ever so slightly, you can see the surfaces are sliding along there. Now if they're rolling bearing pins then you would have a rolling action, a pure rolling action all the way around. So these lobes are in intimate contact with the pins, every one of them is, and so you get a very pure torque output for a number of applications. Okay, so that's stage one. This is what we're going to model. Okay, so the first thing we do in MechDesigner is add a mechanism, because we always build our mechanisms in mechanism editors, and we add a mechanism to a plane. Okay, so the first thing we do is represent these gear reduction with a set of simple gear pairs in MechDesigner. So that's the first step, is to represent the gear ratio with normal gears. So we're going to edit the base part by double-clicking the rectangular outline. I'm going to add a line to the base part by dragging out the line, and I'll just make this point here coincident to the frame axes and make that line horizontal. And at this point it doesn't really matter how long that line is. I'm then going to add a part by dragging it from the pin joint. I'm going to add a motion dimension to that part, and so then we can move it, and I'll add a clock to that, so that will now just follow the machine. So I'll just give this a nice round number for its starting value. It doesn't really matter at this stage what that value is, they're just like round numbers. So there we are, 60 degrees. If I hit the cycle button, then we'll go round and round, and we can go faster if we want, or slower. But again, moving it doesn't really matter at this stage. I'm now going to add another part to the end of this part, and at this stage we can quickly add the gear pair. So I'm going to add the gear pair, and for that we need to select 4 elements. I'll just expand this a bit so you can see what elements we need to select. It's I know what to do, so we select this green line here, and that's will be for the driving gear or the driver gear. This line is going to be in the driven gear. This is going to be the line between the centers of the gear pair, and this is going to be the dimension. And so if we just cycle that now, you'll see that we have a standard epicyclic gear arrangement. Now what we've got to do is rearrange this so we get the proper cycling orbital cycloidal action. So I'm going to edit the gear ratio. I'm just going to check the module of this. So it's module 1, so I just I'm going to put this maybe at 120 teeth, and this is maybe about 110. Whoops. And then make the gears internal and click that and zoom in a bit more. And if I cycle this, you can see that the there's a small shaft in the middle like a crank. That's really going to be our eccentric pin, and then there's the output part is rotating slowly. It has a rotating motion, but it also has a wobbling motion by virtue of being on the end of the crank. But the gear itself, if we measured the angular rotation of the gear, then we would find, relative to the crank, it's going at constant velocity. So we've got to extract that constant velocity out of this arrangement somehow, and we'll do that with the cycloidal gear arrangement. Now at this stage we've got the epicycloidal gear reduction, and what we need to do now is add the pins to the machine frame. So to do that, we just edit the machine frame, and I'll double click the base part, which is the rectangular outline, and now we're editing the frame. And what I'm going to do is add a number of rollers to the frame, and this is a little bit tedious in MechDesigner, but off we go. I'm going to add 12 rollers, 1, 2, 12. Okay, so the first thing we want to do is make all these the same size. Well, first thing, I'll dimension 1, and I'll make that 10 diameter, I think, not too big. And whoops, I'm going to make all these the same size, so quickly just go, and unfortunately I can't control select all of them, adding an equals constraint each time. Next thing we'll do, I'm just going to add lines from a single point. So I'm dragging from the point to the center of the circle. Okay, so we've done that. Now I'm just going to make all these lines the same length. So I'm going to start here, go equal, and I'm going to now make the center of the ball of lines. I might have to filter this to points. So there we are, just put filter on the points and to there. So that's going to snap there. Take off the filter. And now I'm just going to dimension one of the lines and maybe make that 100 millimeters long. And okay, so we're getting there. I'm going to make this line coincident with this, and carry on with the coincidence. I'm going to make this coincident with this also, so it stays horizontal. 1, 2, 3, make this one coincident with that. So we've got 4 all set up. Now I'll add the dimension from there to there, from that to that, and make that 30 degrees. And the same there. Put that point in line with that line. I think we're about there. the sketch would normally go black once it's correct. Maybe I've missed out on one of the constraints somewhere. So let's leave it like that there. So that's step 2. Okay, while we were away, I was just looking why this sketch hadn't gone black, and all I'd forgotten to do is dimension this length of this line here. So I'll do that now, and everything should go black. Okay, I didn't really dimension it because it didn't really matter, but actually it just informs me that the sketch is now fully defined. So we're more or less ready to add the first cycloidal cam. So the first thing I need to do to add any cam is to make the cam follower a profile or a solid. So all I do is select the add profile, select this circle, and it'll become a cam follower. And to make things sensible, I'm going to make this angle 0. So this bit pointing in this direction, it's a very small distance, but the eccentric's pointing in this direction. So this will indicate the hollow of the cam, and this makes it easier for when I want to add the other one. So now all I need to do is add the cam. So the first thing is select the part to carry the cam, and that'll be the cycloidal, well, the epicyclic arm, and then I click the profile, which is going to be the cam follower. Now, it doesn't look much like a cycloidal, but you'll see here there's a start of it, but it doesn't seem to be doing much. So to show it doing all 11 cycles, and as it happens, this will do 1 rev. If I just cycle the mechanism, 1 rev of this crank is actually 1 lobe pitch. And what we want to do is maybe cycle this 11 times within 1 machine cycle. So I'm just going to add a gearbox in here, and right click, add a gearbox, and then connect that in. So the machine timing is now going to go through the gearbox, and you'll see the cam come straight back in. And as I increase that, we should see more lobes round and okay. So we're going around here. Whoops, gone too far. So it's 11 to 1. Okay, so now you'll get a feel. Now we've got the cam profile on the inside and outside, and we don't need it on the outside. So I'm just double clicking the cam, and then going to take one of these off. I always get it wrong the first time. And so that's our cycloidal cam. Whoops, it's going a bit faster now, so I'll just slow that down. And okay, so that's our first cycloidal cam. Now what I'm going to do is check that we don't have any undercutting, and we've got a radius of curvature here that's not going to pinch the roller. So another way of doing that, of checking that, is to look at the cam, and I use the cam function block. I'm going to double click that and associate this cam function block with this cam, and ignore the cam coordinates for a short period. And all I'm going to do now is add a graph, and I'm going to plot the radius of curvature of this graph, and it's cam2, and it doesn't seem to be showing much. Why is that? Let's just look at the yeah, it's a ridiculous number. Maybe it's not showing it properly. Oh no. Okay, let's zoom in a bit further on that. So we've got a 10mm pin. It's probably not going to be much more than 30mm. So I'll put plus or minus 50 as a dimension. And then we can see these lobes here. So you can see the radius of curvature is 20, as in that direction 12. Even 12 is big enough, but I think this is the one oh no, it is this one we're concerned about. As you drag the red cursor, you can see the mechanism move to where it is. So there we are. We're looking at quite close to the 10mm. Now we might have to increase the size of the cam or decrease the size of the pin, but at least we know it's not going to jam. Okay, let's move on to the next step later. Okay, we're ready to add the second cycloidal cam, which is really intended, it uses exactly the same principle as the first one, and it's really there to add a bit more capacity to the gear reducer and also to balance it. While we were away, I snuck in and added a line to the small crank, and that's at 180 degrees and the same length as the crank length. So this points in the equal and opposite direction. So on the end of that, I'm going to add a part, and now we're ready to add the gear pair, the second gear pair. I'm going to select the line in the frame, and when there's more than one line there, it asks me which one do I want, and I think it's this one we need. So I'm going to click that and click this line, and then we have to click the line between centers and then the dimension of that line, and then we click OK. We'll end up with a couple of very small external gears which are tiny compared to the other ones, but I'll just edit the number of teeth and I'll make them the same number of teeth. So I think the other one was 120 and this one was 110, and they were internal gears. And so when we zoom out, we should see equal and opposite gear pairs going around there. So now I'll quickly add the other cam, and I'm going to make this the cam follower for that, for this other cycloidal, and hopefully, because this crank's pointing in this direction for this one, we'll end up with a hollow over here. So I'm going to add select the same part in the middle. So I'm just going to jog that off to make sure I get the correct part. I'm going to select this part as the rewind. I'm going to select this part as the cam, and this as the cam follower. Hopefully they're equal and opposite. So again, I'm going to remove the one of the cams, and I think we've sort of successfully achieved that. And if I cycle this, then we'll see the two lobes counteracting each other, and one lobe is in the trough while the other one is on the crest of the wave. Okay, so now we're ready to extract the constant speed component of the rotors moving slowly in the clockwise direction, and we want to extract that component to an output shaft. So at the moment it doesn't look as if the rotors do go at constant speed, they're sort of wobbling and rotating. So what I'm going to do is add the output shaft, and then we should be able to see that they're moving at constant speed. There is a component which is constant speed. So I'm going to add the output shaft first and add the part, add a pin joint between it and the frame, which is here, and so I'm going to select that point and one of the base points, control select those two, and OK that. So now we've got a pin joint. Now we need to add the motion dimension. So I'll select the pin joint, and then I have to select the line along the frame and a line in the part, and then we should see the motion dimension appear, which we have. Now generally the rotors go clockwise, so what I'm going to do is I've added a gearbox here ready to input to that new shaft, and if I set the initial angle to 0 degrees, and let's just watch it move. Now this is the input shaft is here from the center. Now let's just watch it rotate, and you can see if I slow everything down, you can see that it actually stays parallel with this shaft here, but that shaft is advancing and retarding in position by virtue of its center moving around a circle, but the actual orientation stays fixed with the constantly rotating output shaft that I've just added. So that proves, more or less, that these two rotors have a constant velocity component in the clockwise direction. So that's the first step of delivering the output. So I've modeled the output shaft. We've got to extract the constant angular speed from the rotors. So I'm going to edit the rotor, and I'm going to put in cut some circles into it, cut some holes into it, and this is the first part of extracting the motion. So we need to, it's a bit of a trick actually. So first thing we do is add 4 circles, and then I'm going to draw lines, and I want to put the circle on there, and the radius of these circles happens to need to be twice the eccentricity of the central crank, so that's 10. So, and we do the same on the other rotor. So let's just do this. That looks a bit more like it. Okay. Alright, now we're ready to put the dimensions in for the sketch, and the first thing is to put the angle in between the x-axis of this part and the holes, and that's different to the other set. It happens to be 360 divided by 2 times the gear ratio, and the gear ratio is 11, so divided by 22. We need the radius, and the diameter of the holes themselves need to be 10, so I'll just round that to 10. Okay, the sketch goes black, and I think we're about set. And if I cycle that, you'll see that the holes, there's 2 sets of holes orbiting around each other, more or less. Okay, ready for the next step. What we've got to do now is add to the output shaft a number of pins so that the holes through the lobed rotors can continuously move the pins around at constant velocity. So what we need to do is edit the rotor, output rotor, which is this part here, and I'll just send this to home, and then I'll put in 4 pins to remind me what radius I need. I'm just going to show the other sketches, and I'll just dimension 1, and these have to be in the middle of those 2 other circles. So I think that is also 45. There we go, perfect. So now when I cycle, you can see my new circles encased within the other 2 holes, so the pin has been driven round at constant velocity. Okay, so that's the kinematic design done, so all the parts are in place. Incidentally, the gears are used only to develop the type of motion that we need in order to generate the motion of the wobbling parts, which are the lobed rotors, and by virtue of that motion from the gears we can generate the cam profile. But these toothed gears aren't involved in a lobed or cycloidal gear reducer at all, so don't confuse the two. We just use the gears, toothed gears, to generate the motions that we need in order to generate the cam profile path, so that needs to be said first. So let's develop the solids. So the first thing, to make the cams solid, I first have to make them a polyline, and I use the add polyline command twice on that, one for each cam, and then I can add the profile to the polyline, and do it twice. It's got two cams. Something a bit more pleasant than that blue, and hopefully we'll see things a little bit better now. So now you can see the cams going round. The rollers are very poor quality if you zoom in there, so we need to increase the quality of our shapes, and that's in the General tab of the application settings, and I'll put it round about 2/3 of the way along. So that should be a lot better. I think if I regenerate, there we are, we've got the smooth cam rollers now, one each side. And what I'll do next is add the holes into the lobed rotors, and I'll use these to add holes to the lobed rotors. Okay, so I've already got the circles in there, so I select the circle and then the profile that it's within, and I'll just do these two to begin with, and that one there, and hopefully when I show the solids you can see that they're cut through, and if I cycle through you'll see that they stay partially engaged with each other, and we can put a pin in the middle of that lot. So I'll use that to add a pin and create a solid rather than a hole with that pin, and if we just use the front view again, we should see that pin moving around at constant speed, and that's on the output shaft. So we just need to repeat this and change a few colors. Make sure everything stays engaged. Yep, looks as if it does. So now I'll add the pins, the 4 pins. Okay, let's see how that looks. Looking a bit better. And I'll put the eccentrics in so you get a feel for that. So that's just a couple of circles. So let's edit the shaft. Going to hide all the existing sketches. Put a circle. Okay. So there we'll go around with some colors on for those and some solids. Add that. Let's just edit it and get a feel for it. Let's change its color first to. So now we have a feel for the rotating input shaft here. So that's rotating, and it has an eccentric disc, which if there were no rollers around the outside, then the disc would just move in an orbit, but because of the engagement with the rollers, it's forced to also cycle itself, and then that motion is imparted to the low speed shaft at the output by engaging with the pins here. So we can improve the layering of that to get the design much better if we wanted to. So next up I'm going to show you how to get the coordinates out for these so we can cut them on a CNC machine. Okay, this step I just want to show you how to get the coordinates for the cycloidal cam rotor into SOLIDWORKS. It's quite easy. We've already added a cam data function block because earlier on we measured the internal radius of the cam to make sure that the roller wouldn't bind on the minimum radius of the cam. So we found that the minimum radius was about 12 and the roller is about 10 radius, so we're okay there. So I'm going to use the same function block and just open that, and the cam data function block opens. Now I'll just reduce the screen size and I'll just clear the screen. So this is how it would normally open, and this form is already associated with the cam, so I'm just going to rebuild it and to 1,000 points, and it's calculated at 1,000 points fairly quickly there. I could do 10,000 points nearly as quickly, but let's just rebuild that. So we want to export 10,000 points. We can do that, but I don't think that's necessary. Let's just keep it to 1,000 points, and I will rebuild again. And then it's a simple job just to press the button here to export the data to SOLIDWORKS. So at this point in time it's compiling data, and there we are, the profiles in SOLIDWORKS. So now we can use this to create a sketch. So I'm going to create a sketch on the front plane, add a sketch, and I'm going to convert the entities of this profile into solid, into a sketch or a spline, and then I'm going to extrude that by 10 millimeters, and there we have it there. And I can quickly add more features onto that. So I'm just going to go the normal view to that and add a sketch to the front of that, maybe add a circle, and I will make that a standard size for the external for a bearing to mount onto it, maybe 60 millimeters or 50 even, and extrude that through the middle of that. So let's just increase the size of this so we can see what's going on. So there we are. So that's the cam. Maybe to make things look a bit prettier, I'll put a couple of chamfers on it, and maybe on the back side also. There we are. So there we are, that's the cam there. Now we can re-import that cam onto this part. So I'm just going to look at the front view. I'm going to hide the solids. I'm going to send the model to home, and then just drag it off slightly, or cycle it on a bit, so I know which part's which. I think it's one of these, so let's just grab one of these. This CAD line of that. So I'm going to read the path of the current part, and that's called Cycloidal cam, 1000 points, and I'm going to import it. And when this button deactivates, we will find that the cam will be in here when we show the solid again. Okay, so what I'm going to do first is remove the profile from both of these. Delete that. So when we show the solids in this model, we should be able to see everything is moving as it should be. Let's just zoom right into the roller, the fixed roller with which the lobe rotor is engaged, and we can see if we cycle things on and slow it right down, whoops, you can see the contact is made exactly with the fixed roller. So we can continue importing solids and creating solids, putting the holes in the shaft actually, and importing more solids, doing the detailed design. But the most important thing is the lobe rotor design, and that is one of the most difficult parts to get right and get the details right of that with coordinates. We'll leave it there. Thank you very much. At this point, I would really like to encourage you to contact us at sales@psmotion.com to request a free download and a trial of MechDesigner so you can see how you can use it in your applications. The MechDesigner is normally used for modeling complete machines. This is just another example of how MechDesigner is powerful enough to be used in a number of applications. So get in contact anytime soon. Thank you.